So we are going to continue to discuss something we ended chapter 29 on in the beginning of chapter 30. So we already discussed the idea that you can vary the current in one coil, and that can induce an EMF in another coil. So we introduced that concept when we discussed Faraday's laws in terms of electric fields. So we're starting with that exact same setup here, where I have coil 1 here, where I'm going to change the current, and that's going to induce an EMF in our second loop here. So I'm going to start with Faraday's law, the idea that the induced EMF in coil 2 is equal to the negative of the number of turns in coil 2 times the change in flux through coil 2 with respect to time. Now here's where we're going to deviate a little bit. I'm going to define a constant. And it's not a constant in terms of something you look up in a constant table, but it's something constant for a particular system. So we're going to say that the number of coils in our second coil, the one experiencing the induced EMF, times the flux through it, is going to be equal to something we're going to define in a second, but we're going to call it a proportionality constant for now, times the current from the first coil. And remember, the first coil is what's actually causing what is happening in the second one. And remember, we're using little I here, so that I is varying with time. Now I'm going to divide this setup here by dt. Alright, and then if you'll notice here, this here and this here are the same thing, missing a minus sign though. So I can rewrite that the induced EMF in coil 2 is equal to the negative of our proportionality constant times di, and remember di is from the first coil divided by time, where this proportionality constant is going to depend on the geometry of the coil. And if you think back to the example we did in the previous chapter where we had the solenoid with the current varying in it, there's a whole bunch of things in the magnetic field equation, like the magnetic constant, the number of turns, the length of the coil, all of those things, the area, all those things that were inherent to the coil itself, which would be fit into the geometry of the coil. And then everything else, and the last thing in that particular equation was di dt. So essentially you've hidden a lot of the constants for that particular coil inside of this proportionality constant. It depends upon the geometry of the coil. And we're going to refer to this proportionality constant as mutual inductance. And this is going to have a new unit called henries, abbreviated capital H. Now, one thing I do want you to be cautious of is that this flux in here, even though we say it's the flux through coil 2, remember that it's the magnetic field from coil 1 that's actually causing that. So you have to be careful when you're solving for that magnetic flux there that you're getting the information for the correct coil.